Welcome to this video on thermodynamics. We will explore various enthalpies, spontaneity, entropy, and Gibbs free energy. Let's examine different enthalpy changes in chemical processes, including formation, combustion, atomization, and bond enthalpy. Notice how energy flows and molecules transform in these reactions. Consider the combustion of methane. The change in internal energy, delta U0, is given. Can you determine the relationship between the change in enthalpy, delta H0, and delta U0 for this reaction? Here are some practice questions covering enthalpy of formation, combustion, atomization, and bond enthalpy to test your understanding. The standard enthalpy of formation is for forming 1 mole of a compound from its constituent elements in their standard states. Atomization is always endothermic, requiring energy input. A C equals C double bond has higher bond enthalpy and is stronger than a CC single bond. A spontaneous process is irreversible and may only be reversed by external action. Some spontaneous processes, like sugar dissolving, need no initiation, while others, like coal burning, require an initial push. Is a decrease in enthalpy a sole criterion for spontaneity? Exothermic reactions, with delta H less than 0, often are spontaneous. Endothermic reactions, with delta H greater than 0, can also be spontaneous. A decrease in enthalpy is a contributing factor, but not the sole criterion for spontaneity. Entropy and temperature also play crucial roles in determining whether a reaction will proceed naturally. The combustion of methane is an example of an exothermic and spontaneous reaction. It releases significant energy, driving the process forward. An example of an endothermic and spontaneous reaction is the dissolving of ammonium nitrate. It absorbs heat from the surroundings due to a large increase in entropy. Entropy, symbolized as S, measures the degree of randomness or disorder in an isolated system. Increasing disorder is key to understanding spontaneity. A key conclusion about entropy and spontaneity is that any process where the total randomness of the universe, system plus surroundings, increases is a spontaneous process. For irreversible processes, the change in total entropy is greater than 0. For a reversible process at equilibrium, the total change in entropy of the universe is 0, meaning the entropy of the system and surroundings balances out. Comparing reversible and irreversible processes, the total entropy change is 0 for a reversible process, indicating equilibrium, but positive for an irreversible, spontaneous process, showing increasing universal disorder. The second law of thermodynamics has common definitions. Spontaneous processes are thermodynamically irreversible. Also, it is impossible to convert heat completely into work without producing changes elsewhere. Further definitions state that a spontaneous process is accompanied by an increase in the total entropy of the universe. Additionally, heat cannot transfer from a colder to a hotter body without external help. Gibbs free energy can be thought of as, quote, useful energy or doability energy. It is the energy that is free and available to perform work. Processes move spontaneously from high Gibbs energy, or lots of doability, to low Gibbs energy. Moving uphill, or to higher energy, is not spontaneous and requires work or a push. Simple examples illustrate this. Ice melting on a hot day is spontaneous. Cleaning your room is not spontaneous and requires your work. Gibbs energy, G, is a thermodynamic function defined by the equation G equals H minus Ts, relating enthalpy, temperature, and entropy. A spontaneous process has a change in G less than 0. This scene continues the discussion on Gibbs energy and spontaneity. Here we are focusing on the relationship between Gibbs energy and whether a process is spontaneous. This scene emphasizes the criteria for spontaneity based on the change in Gibbs energy. We are still exploring the concept of Gibbs free energy and its implications for reaction spontaneity. This scene provides additional information regarding the connection between Gibbs energy and the direction of a process. The relationship between thermodynamic variables and spontaneity remains the focus of this scene. We continue to examine how Gibbs energy determines if a chemical or physical change will occur naturally. This scene reinforces the understanding of Gibbs energy as a measure of a system's capacity for non-expansion work. The connection between thermodynamics and the concept of useful work is highlighted here. So we conclude that reaction becomes spontaneous at temperature greater than 2000 Kelvin. In this scene, we review the key factors that influence spontaneity in terms of Gibbs energy. The relationship between Gibbs free energy, delta G, and the equilibrium constant K helps us predict both the spontaneity of a reaction and the direction in which the reaction will shift when it is at or near equilibrium. Practice questions on enthalpy for the exams. Thank you for watching this video on thermodynamics, covering enthalpy, entropy, and Gibbs free energy.